Last lesson in Chapter 7. We are going to try to wrap all of this stuff together, these volumes of solids of revolution, and we're going to try to tie disk, washer, and shell together. Which one works, how does it work, and just try to have one lesson here that has everything in one place with some comparisons. So find the volume of the solids formed by revolving the area enclosed by the graphs, by the given functions about the given axis using both variables. So what I'm going to do is we are going to use this region, the region that you're looking at right here, y equals x squared plus 1, y equals 0, x equals 0, x equals 1. And we're going to revolve this around four different things. The y-axis, the x-axis first, and then on the second page, x equals 3 and y equals 4. So we're going to revolve this thing. Two of them I think you're going to, I would guess at this point in your learning, you're going to feel pretty comfortable with, and two of them you're going to feel like are pretty difficult. So let's start. Okay, again, we're going to work as much as we can on a visual. We're going about the y-axis the first time. The best thing you could do is give yourself that visual. Where am I taking it? So we're going about the y-axis. And you'll notice for each of these we're going to set up both an x integral and a y integral. X integral and a y integral. So, let's see. So this first one, if I'm using x's, I would take my rectangle and I would put it in vertically. Okay? So vertical rectangle. If it goes in that way, I'm supposed to use dx's. Well, what will that mean? If I revolve that yellow rectangle, it looks like I'm going to create a shell. So I'm looking at a shell method. So when I go to set up my shell method, let's immediately go volume. Let's set up the template. It's 2 pi integral from somewhere to somewhere. I don't know where. I need a radius. I need a length. And I'm supposed to use dx's. So if I set that up, let's see, my integral. What have I got? Well, it would probably help here to label the coordinates of our point. So this is the origin. This is the point 0, 1. This is the point, let's see, so if I take x equals 1 and plug it into y equals x squared plus 1, I'm going to have the point 1, 2, and then this is the point 1, 0. So those points are going to help inform us on what happens with the x's and the y's. So let's see, first integral. My first integral is going to go from x equals 0 to x equals 1. I need enough x's to cover that region. And my radius will be the distance from this rectangle over to the axis I'm revolving it around. That's going to vary. It's going to be a horizontal distance, and we're supposed to be using x's, so it's a distance from the x-axis or from the y-axis to the right over to the curve. That is going to be a plain old ordinary boring x for the radius. This x would be our radius. And the length of that rectangle would be the distance, or would be the distance from our f of x down to the graph. That distance would be what our x, it's a vertical distance using x's. That would be x squared plus 1. Okay, so there's your shell method. Now what happens if I go to use dy? Well, if I put a rectangle in using dy, it's going to look like that, but that rectangle will only be good until the curves switch. So we're going to need two integrals here. So anytime we use dy in these four examples, we're going to end up needing two integrals. So we're using dy's, which means eventually, at some point, I'm going to need to get x by itself in this equation. So y minus 1 is equal to x squared, so that means x is equal to plus or minus the root of y minus 1, and it looks like since we're using the right half of that graph, we would only want the positive root of y minus 1. Now we'll see how that plays in. So we're going to need two integrals. This bottom integral is going to, is there a gap between this, the end of this rectangle and the axis it revolves around? No, there's no gap, so that is a disk method. So the integral, first integral is going to be a disk. So let's set up our template. And the second integral, is there a gap between this point and the axis we revolve it around? Yes, there is. So the second one is going to be a washer. So let's set up that template. Oh, sorry, I forgot pi over here. Shame on me. Pi integral from I don't know where to I don't know where of a quantity squared minus another quantity squared dy. Now all we have to do is figure out what those quantities are. Well, so that my first integral starts at y equals 0 and goes to y equals 1. So we're integrating 0 to 1 for y's. Second integral starts at y equals 1 and goes up to y equals 2. All I have to do is figure out the length. How long is this rectangle right here? Well, I think it's always going to be the same length as long as we're between y equals 0 and y equals 1. That length is the distance from this line over to the y-axis. That distance is always going to be 1. And in my second rectangle, this one up here on the top, we're going to have a gap, so I need my outside radius. Outside radius goes from the furthest point on that rectangle over to the axis we're revolving it around. What is that distance? Well, that distance is always going to be the same no matter how we slide this green rectangle. As long as we're between y equals 1 and y equals 2, that outside radius is going to still be 1 for the same reason that this one was 1. The inside radius is the distance from the closest point on that rectangle to the axis we're revolving it around. What's that distance? Well, it's going to vary, and since it varies, it better have a variable in it. It's a horizontal distance, and we're using y's. So that distance, the distance between those two blue dots, would be f of y. What's f of y? The square root of y minus 1. Square root of y minus 1. So all that, we're 1/4 of the way done with this lesson. So we've got that first one figured out. We can use our calculator to figure out our integrals. That's not going to be our big issue. Our big issue is getting them set up. So let's do it again. Second problem, x-axis. What's going to be different? Revolution. Now we're going around this thing. X-axis. So let's say we use dx. This time if we're going to use dx, and we go to put our rectangle in, just like we did a second ago. Now when I revolve that thing, I'm going to make either discs or washers. Is there a gap between the bottom of this rectangle and the axis we revolve it around? No, there's not. This is going to be a disk method. So disk method, set up your template. Pi, integral from I don't know where to I don't know where of a quantity being squared with a dx on it. What's our integral? Well, my x's are going from 0 to 1. The length of that rectangle for my radius is your x squared plus 1, so it's your f of x. For my dy, here we are again, we're going to need two integrals just like we did up there in that previous problem. So let's put rectangle in. If I put a rectangle in this way and I revolve it, this time I'm going to make shells. But I still need two integrals because I'm using dy's. So if I go to do this, if I use dy, I'm going to first need a shell. And my first shell is going to go from y equals 0 to y equals 1. What's my radius? My radius is the distance from this green thing down to the axis I'm revolving it around, which is a vertical distance using y's. So that radius is going to be y this time. And how long is that rectangle? Well, for the same reason that up here in this previous problem that distance was determined to be 1, it's still going to be 1. Again, distance between here and here is always the same. It's going to be 1. Okay, we have a little dividing line that takes place right about here before we jump to our second rectangle, this one up here on the top. This one, of course, is going to be more complex. So I'm still going to be, when I revolve that thing, I'm still going to need shells. So my second integral is going to also be a shell. This one's probably going to be a little bit more fun, though. Integral from, well, this one's going from y equals 1 up to y equals 2. And now I'm going to set up my shell again with a dy. I need a radius. What's my radius this time? My radius this time is the distance from here down to the axis I'm revolving it around. Well, what's that distance? It's a vertical distance. It's a distance from the rectangle down to the axis we're revolving it around. Some people will say, well, that should be y minus 1. No, it shouldn't. It's still y. It's still that vertical distance. Just like the green one was a vertical distance, the pink one's a vertical distance also. Well, how do you account for the fact it doesn't start until y equals 1? I account for that with this number right here, as opposed to this one that started with 0. This new integral starts at 1, and that's why this new radius is also y. The green y is smaller than the pink y is, But because of the bounds on the integrals, it takes the rest of those things into account. Now, how long is this green rectangle? Well, that green rectangle is the difference between the distance between the two red dots, which is 1, and the difference between the two blue dots, which is your f of y, which is that square root of y, of the quantity y minus 1. So here we are, root of y minus 1. So there's my revolving around the x-axis. Now we get for the more exciting ones. The more exciting ones, a lot of us are getting better at the x-axis and the y-axis. What happens when we revolve them the wrong way? What happens if we go the other direction? So here we are, same exact thing, but now we're revolving around x equals 3. So x equals 3 is out here someplace. X equals 3 we're revolving around this time. So now when I go to use dx, I put my rectangle in vertically. If I revolve that yellow thing around that yellow axis, I'm going to make shells. If I go to make shell, integral 2 pi. X's are supposed to still go from 0 to 1. I need a radius. I need a length. I've got a dx. What's that radius? Normally my radius goes from my rectangle over to the left to the x-axis, and we call that distance x. Do we want to revolve this that yellow rectangle around the y-axis? No, we don't. We want to take it the other way. So our radius is the difference between that whole thing 3 over to the y-axis and that red x over to the y-axis. So my radius this time is going to be the difference between the 3 and the x. How long is that rectangle? That's still your fx. It's still your x squared plus 1. So the big difference is the part that's in the green right there, and that's because we're not taking our rectangle that we drew toward the x-axis or the y-axis. We're taking it the opposite direction, and that's why we have a difference in our radius. All right, now when we go to use dy, same idea. 2 integrals, ho-hum, I've done this a few times before. So the first one is going to be, it looks like a washer, pi, integral, quantity, something being squared minus something being squared with a dy on it. The integral looks like y's are going to be going from 0 to 1 just like they have been all along for that first integral. Outside radius, distance from the furthest point on my rectangle over to the axis I'm revolving it around. What's that red distance called? That red distance would be 3. Inside radius goes from the closest point on my rectangle to the axis I'm revolving it around. What's that distance? That's going to be the difference between the 3 and the 1. So that's going to be 2 plus the integral with a pi in front of it, going for the rest of the y values, which start at y equals 1 and go to y equals 2. We're doing it looks like another washer method. But this one's going to get a little bit more exciting. Let's do the red dot thing. If I do the red dot thing, furthest point away from my axis I'm revolving it around to the axis I'm revolving it around, we're used to this distance being my f of y. Are we revolving toward the y-axis? No, we're revolving away from the y-axis. So the distance between these 2 red dots is the difference between all of 3 units, yellow dotted line over to the y-axis, and the blue f of y. So what I want for my outside radius is the difference between that 3 and my f of y, which is the square root of the quantity y minus 1. And my inside radius is the distance, I'm going to do black this time, the inside radius is the distance from the closest point on my rectangle to the axis I'm revolving it around, and that, just like the one that the integral written above it, is still going to be a 2 and always be a 2. Last but not least, revolving it around y equals 4. Well, where's y equals 4? Y equals 4 is up here someplace. Y equals 4. That line right there, we're revolving it around y equals 4. So if I use dx's, if I'm using d-axis, put your rectangle in. Going that way. We're going to make either discs or washers. Is there a gap between here and the dot and the orange line, orange dotted line? Yes, there is. So this is going to be a washer. So set up your integral. Pi integral from somewhere to somewhere. What's the somewhere? X equals 0 to x equals 1. Outside radius squared minus inside radius squared. The dx in it. Outside radius, furthest point away. Axis I'm revolving it around. How far is that? It's always going to be 4. Inside radius, closest point on the rectangle to the axis I'm revolving it around. What's that distance? That distance varies, so it's going to have a variable in it. So from this blue dot down to the axis would be the square root of x plus 1, or it would be x squared plus 1. From this blue dot up would be the difference between all of that orange 4 and my f of x, which would be x squared plus 1. Anytime you're revolving it away from the x-axis or the y-axis, you're going to have some sort of a difference involved there. And when we go to use dy's, that looks like a shell. 2 pi integral from 0 to 1, radius, length dy. What's my radius? Normally my radius would go this way, and that would be a y. We're not taking that green rectangle toward the x-axis. We're taking it the opposite direction. So my radius would be the difference between this 4 and that y that we normally have. Again, we're going the wrong direction. We're not revolving it toward the x-axis. We're revolving it the other direction. How long is that rectangle? That rectangle would be always 1 unit long. And to finish this show off, plus another shell, 2 pi integral from y equals 1 to y equals 2. I need a radius, I need a length with a dy. What's my radius now? If I put this rectangle in here, what's this distance? That distance is a y. Are we revolving that rectangle toward the x-axis? No, we're not. We're taking it the other way. So it must be the difference between 4 and that y. How long is that rectangle? The length of that rectangle would be the difference between this 1 and that f of y, which was the square root of y minus 1. So what we got here is we've got 4 examples of how we made this thing go, and with 4 different regions, or with the same region revolved 4 different ways. And hopefully now we got a resource that we can come back to and look at, because if you can do those 4 things, you can handle just about any disc, washer, or shell problem.